Hello. In the last lesson we talked about the rocks and minerals that make up the crust of the earth. Today we will look at what makes up the interior of the earth. Well, how do we know what is inside the earth? Hundreds of thousands of kilometers deep within the inside of the earth. Now, has anyone gone there? What is the deepest from the surface that any man has gone? Well, maybe a couple of miles. What is the diameter of the earth? 12,800 kilometers. That means to reach the center of the earth, one has to go 6,400 kilometers deep. How do we know what is inside the earth? What is at the center? What is surrounding it? What is inside the earth? Do we know exactly? Well, if a doctor wants to know what is inside your body, very often he doesn't break you open. Very often a doctor has tools like send ultrasound, and when you send a beam of ultrasound, the way they reflect, the way they transmit, give the doctor information about the conditions of our inside body. And sometimes, some doctor will keep their hand and knock. Is that right? Now, how the sound behaves when it transmits inside and reflects gives the doctor some indication of what is inside. In the same way, in order to find the structure of the interior of the earth, we use informations that are gathered from earthquake waves. The information about the earth's interior has been largely obtained from earthquake waves. Seismic waves radiate outward from where an earthquake is formed, and it goes in all directions. It goes to the surface and it goes through the inside of the earth, which can be detected on the other side of the earth. Now, there are three main kinds of earthquake waves. We will discuss these waves once again in detail later, but let's look at these three kinds of waves. The first type of wave is called longitudinal waves or compression waves. In other words, this kind of waves will set the particles of the Earth's crust into compressional motion of this type. You see that? And this motion is passed on from one part to the other. Now, the important thing about this is that this kind of wave can actually pass through rocks and solid and liquid materials below. So these compressional waves can go through the solid materials and liquid materials. Now, the second type of wave is called the transverse wave. You see, the transverse wave is the particles of the material are made into up and down vibration when energy is transmitted along the surface. It's a big difference between longitudinal wave and transverse wave. How does longitudinal work? Longitudinal waves make the particles of the medium vibrate back and forth, causing compressions, and the energy goes along the surface. Whereas transverse waves make the particles vibrate up and down, and the energy goes at right angles to it. Now, transverse waves cannot pass through fluids. It can only pass through solids. So, if transverse waves cannot be detected at one point, the conclusion is that there has been some liquid along the path where it cannot pass through. There is a third type of waves called the surface waves, much like the water waves that moves across the solid surface of the earth and are the slowest of the waves. Well, these are the two main types of seismic waves. Well, our present day understanding of the interior of the earth, which have been obtained from seismic waves, is we have an inner core mainly made of iron. We have an outer core which is of liquid iron. We have another layer called the mantle, and then you have the crust, and of course the atmosphere. So look at that once again. We have a solid inner core mostly of iron. We have a liquid outer core mainly of liquid iron. Then we have mantle. Mantle is actually the biggest part of all this. And the crust, we talked about the crust that is made up of the rocks and minerals, and of course the atmosphere. So using data from seismic waves, scientists are able to map the interior of the earth. And this is what the map looks like. The earth is divided into four main layers. The inner core, there you are, the outer core, the mantle, and the crust. The atmosphere is, of course, a shell surrounding the earth. Now, let's have a look at the core. What is the core? In fact, the core was the first internal structure element to be identified. That was the first structure to be studied. Well, why was the core the first structure to be identified? It was discovered in 1906 by R.D. Oldham from his study of earthquake records, and it helped to explain Newton's calculation of Earth's density. You see, the density of Earth is about 5.3 gram per milliliter, but the density of the crust is very low. It's about 2.2 gram per milliliter. So where does the big difference come from? It has to be the fact that the core is very dense. So the indication that core is a dense solid material made of iron actually came from the study in 1906. And of course, it was aided by the seismic waves. The outer core is presumed to be liquid. The outer core, this yellow color, is presumed to be liquid because it does not transmit the transverse wave. You see, if a transverse wave cannot pass through a medium, it's an indication that it is liquid. And also because the velocity of compressional waves that pass through it is sharply reduced. You see, when a longitudinal wave or a compressional wave pass from a solid to a liquid, its speed changes. So the sudden change in speed is an indication that the outer core is a liquid. So look at the way we get information about the interior of the earth. Although we cannot look at it, we cannot go there. Well, the inner core is considered to be solid because of the behavior of the P and S waves passing through it. So the behavior of the structure of the inner and the outer core, mainly we know because of the behavior of the seismic waves that either pass through or does not pass through the core. The S waves do not travel through the core, but may be converted to another type of waves called the K waves on entering the core. But we will not go into the details of that. Data from earthquake waves and laboratory experiments on melting and alloying of iron indicates that the core is composed principally of iron. So most of what the core is made up of is iron, with about 10% alloy of oxygen or sulfur or nickel. Well, this is the understanding we have of the core. Alright, let's now go and have a look at the mantle. Now we talked about the inner core and the outer core. Let's now talk about the mantle, which is a very important part of the interior of the earth. Now, this is the solid inner core, this is the liquid outer core, and look at the mantle. The mantle is by far the largest in volume of the internal structure. The mantle is between the outer core and the crust. This shell takes up about 80% of the Earth's volume. You can see that's the largest part of the interior of the Earth and 2/3 of its mass. Now, our knowledge of the upper mantle, we will be talking mostly about the upper mantle here. Our knowledge of the upper mantle, including the tectonic plates. Now, that's an important term that we must be talking about as we go on. Tectonic plates is actually the crust of the earth. You see, the crust of the earth is made of rocks. And the crust is actually broken in several places. And the crust is actually an arrangement of these broken pieces, like the puzzle pieces that we assemble. And these are the tectonic plates. And these tectonic plates are actually sitting on the upper mantle. Alright? So our knowledge of the upper mantle, including the tectonic plates, so the tectonic plates, which is actually part of the crust, is the upper layer of the mantle, is derived from analysis of earthquake waves, heat flow, magnetic and gravity studies, and laboratory experiments on rocks and minerals. In fact, what we know about the mantle and the crust is based on all these kind of experiments that have been done in the past 100 years or so. Alright. Now, studies of the material ejected, volcanoes gives us a good indication of what is inside the earth, because volcanoes very often spit out materials from inside. Is that right? Yes. So a good indication of what is in the mantle can be obtained by materials that come out of volcanoes. So studies of materials ejected from volcanoes suggest that the mantle is predominantly composed of ferromagnesian silicates. I hope you remember what we talked about in the last class. Ferromagnesian silicate, which is olivine. That particular rock material is predominantly what the mantle is made of. The lower mantle below the transition zone. So the mantle, we will be sort of talking about it as the lower mantle and the upper mantle. You see, the lower mantle will be around 3,000 to about 3,500 degrees Celsius. It's very hot. And as you come higher and higher, the temperature decreases. And you remember, when you have a material that is very hot and fluidy, there will be convection currents inside. What is a convection current? Well, hot regions becomes less denser, and the less denser regions will rise, and the cold regions will sink. And this is one of the most important things that goes on inside the mantle. Now, the lower part of the mantle is very hot and very fluidy. It begins to rise slowly, and as it rises, it radiates and gives up the heat, cools down, and then slowly sinks back. What that means is the mantle, the upper part of the mantle, is in a continuous state of motion. The convection currents will make the mantle move slowly. What does that mean? The crustal plates, the tectonic plates are actually carried by the upper mantle are also moving. Now look at the way the earth is a dynamic object, is continuously being shaped and reshaped by what is happening inside the earth. Alright, so being relatively cold, the crust is rocky and brittle, so it can fracture in earthquakes. See, when there is an earthquake, the rocks being very brittle and cold, you know that a material, when it is very cold, is very brittle. It can break very easily. Now, try putting a plastic sheet in your freezer, and a couple of days later, take the plastic sheet and give it a big bang with a hammer. It will break. Whereas when the plastic is hot, it will not break. You see? In the same way, a rock, when it is very hot, it will not break very easily. But cold rocks are brittle and break very easily. And that is one of the reasons why the tectonic plates are broken pieces of large rocks. So there are differences in the crust that make up the continent and the crust beneath the oceans. So when you look at the crust that make up the continent, the landmass that we all live in, and the crust that is underneath the ocean, they are not exactly the same. There are some differences. The oceanic crust is much thinner than the continental crust. So you must distinguish between the crust that is underneath the oceans and the crust that forms the continent. The continental crust is actually thicker than the oceanic crust. Seismic waves move through the oceanic crust faster than they move through continental crust. You see, although the oceanic crust is thinner, it's actually more denser than the continental crust. So seismic waves actually pass through it faster than what it does on the continental crust. Now the two crusts are made of different kinds of rocks. The continental crust is less dense. The granite type rock with a density of about 2.7 gram per centimeter cube. So the continental crust is actually less dense. It's about 2.7 gram per centimeter cube. Whereas the oceanic crust is much more denser. It's about 3 gram per centimeter cube. So the oceanic crust being much denser, the earthquake waves will pass through much faster. You see, longitudinal waves, sound waves are longitudinal waves. Sound will pass through a material like steel much faster than it passes through air. You see, as the density of the material increases, sound will pass through it much faster. The same way as the density of the crust increases, earthquake waves will pass through it much faster. And that's the reason why the earthquake waves travel through the oceanic crust faster than it does through the continental crust. The continental crust floats in the upper mantle. That's something that we talked about already. The continental crust is actually floating above the sea level, and the oceanic crust floats in the mantle far below sea level. And both these crusts, the oceanic crust and the continental crust, are actually floating on the upper mantle. Now here I have the crust and the mantle. Now what is the boundary between the two? The boundary between the crust and the mantle is marked by a sharp increase in the speed of seismic waves. So as the seismic waves moves from the crust to the mantle, there is a considerable change in the seismic wave speed. That means there is a considerable change in the density and the makeup of the material. So the mantle is mostly fluidy. It doesn't mean it's a liquid. Well, it's a solid with very high temperature. It's like a plastic that you can actually shape and reshape. The boundary between the mantle and the crust is actually called Mohorovičić, or simply moho. We will call it the moho. So look at the moho here. This is the moho, the boundary between the crust and the mantle. And you can see the oceanic crust and the continental crust, the difference in this diagram. Now, what are the tectonic plates? The tectonic plates are the plates that make up the crust. So the tectonic plates are made up of the Earth's crust and the uppermost part of the mantle underneath it. So the tectonic plates are actually partly made of the crust and partly made of the upper mantle. Is that right? So tectonic plates is partly the upper crust and partly the crust and the upper mantle. Now, if this is, say, the tectonic plate, now the part of the crust, the upper mantle, the part of the mantle which is closer to the crust is called the asthenosphere, the upper mantle. All right. Now, together the crust and the upper mantle, this is the crust and this is the upper mantle. Together the crust and the upper mantle is called the lithosphere. That means the tectonic plates are actually made by this layer called the lithosphere. And they extend about 80 kilometers deep. So the lithosphere is about 80 kilometers deep. The lithosphere is broken into giant plates that fit around the globe like puzzle pieces. If you look at this diagram, it is shown here how the lithosphere is broken into pieces and they fit together like puzzle pieces. And one of the interesting thing and sometimes disturbing information is that these pieces of huge rocks, or what we call the pieces of lithosphere, called the tectonic plates, are constantly in motion. Why? Because this tectonic plate is actually resting on the top of the mantle. We call that the asthenosphere, the upper mantle. The lithosphere is actually sitting on the asthenosphere, the upper mantle, and because of the convection movement inside the mantle, the upper mantle is transporting the lithosphere on top of it. So these tectonic plates are continuously in motion. So the puzzle pieces move a little bit each year, not very large motion, but very small motion. The puzzle pieces move a little bit each year as they slide on top of somewhat the fluid part of the upper mantle called the asthenosphere. Alright, that picture has to be clear as we move on. Now the asthenosphere is solid even though it is very hot. You see, when you heat a solid to a very high temperature, it becomes almost a semi-solid, not quite a liquid, but you can actually reshape, you can shape it the way you want, or we say it is exhibiting plastic characteristic. Actually, that is what happens in the case of the upper mantle. So the asthenosphere is solid even though it is very hot. The temperature at the upper level is about 1600 degrees Celsius due to the high pressure from above, and the minerals are really ready to melt. The minerals in that rock are really ready to melt and become ductile. What is the meaning that something is ductile? If a substance is ductile, it can be bent easily, it can be shaped easily, it's got some plastic characteristic. Like a silly putty, you know, you work with this putty to shape into different playing things. That's right. That means it's ductile and can be pushed and deformed like silly putty in response to the warmth of the earth. When subjected to pressures, you can actually make this change its shape. Although it is solid, it exhibits the characteristics of a semi-liquid. All right. Now, the flowing asthenosphere. Now, this is the asthenosphere. When I say flowing, it's about few centimeters per year. So the flowing asthenosphere carries the lithosphere. Remember, lithosphere are the tectonic plates of the earth, including the continents on its back. So the continent where we are living is actually continuously being transported by this slight motion of the asthenosphere. Is it frightening? Well, of course. I told you some time ago that our life is at the mercy of nature. So all these things are part of life on earth. Let's talk about the plate tectonics. The plates consist of the outer layer of the earth, which is the crust, and part of the upper mantle, and we call that the lithosphere. Is that right? Lithosphere is made up of the crust and the upper part of the mantle, and we call that the lithosphere. So plates, the tectonic plates are actually the lithosphere, which is cool enough to behave as a more or less rigid shell. So the tectonic plates are cool enough to behave like a rigid shell. In other words, when you subject it to stress and strain, it can break. Occasionally, the hot asthenosphere of the earth finds a weak place in the lithosphere. So wherever there is a break in the lithosphere, the hot asthenosphere, which can behave like a liquid, will creep in. You see? And that is the origin of volcanoes. So occasionally, the hot asthenosphere underneath the lithosphere finds a weak place in the lithosphere and rise buoyantly as a plume or hot spot, forming volcanoes. So volcanoes is the result of the asthenosphere finding a weak spot in the lithosphere and escaping through the cracks, coming out on the surface. Now here I have illustrated that. Now this is the tectonic plate, and you can see a crack there, and the asthenosphere here comes out and spreads, and this is called the spreading center. So the oceanic plates, and look at the convection current in the mantle. The very hot region of the mantle rises and it cools down and sinks, and in the process that liquid mantle will find a weak spot in the crust, in the tectonic plates or lithosphere. It will then find a way to come out. The satellite image shows the volcanic islands of Galapagos hotspot. Now these are hotspots, and these hotspots are where the mantle brings out its material, and these are volcanic eruptions, and we have a number of those on the surface of the earth. Our earth is still a volcanically active planet. And if you look at this picture, it shows you where the volcanic activities are most dominant. Now, what does this picture actually tell you? If you can now map the areas where these kind of volcanic activities are present, that is quite an indication of where you have breaks on the lithosphere. In other words, these are actually plate boundaries. Is that right? Yes. So the tectonic plates, which is made of the lithosphere, shows breaks along these areas where volcanic activity is detected. That means this traces out the boundaries of the various plates. Now, how many plates are there? You can see the plates, the lithosphere is broken into so many pieces, and they are all fitting together to form the crust. And this is quite a good indication of how the tectonic plates actually look like. So the map above locates earthquakes around the globe, and they are not only evenly distributed, the boundaries between the plates grind against each other. You see, because of the motion of the mantle below, these plates grind against each other. Sometimes they hit against each other, wanting to push one away from the other, and some other times they grind sideways. See, like that, producing most earthquakes. In fact, the reason for most of the earthquakes is the relative motion between these plates. Now, the lines of earthquakes, which are these? The lines of earthquakes help us to define the plates. So, geologists have been able to map the tectonic plates by using the areas where the volcanoes are more active or earthquakes are more active. Earth releases its internal heat by convecting. I talked about that. What is the meaning of releases its internal energy by convecting? It means the earth, the interior of the earth is very hot, and that hot part will rise. When it comes to the surface, it begins to radiate energy. It cools down and then it sinks. You see, this is how the earth cools itself or releases the energy, by convecting or boiling, much like the pot of pudding on the stove. If you watch how a pot of pudding boils, it's exactly the same way the mantle behaves. Now, hot asthenosphere, the hot asthenospheric mantle rises to the surface and spreads laterally, transporting the oceans and continents on a slow conveyor belt. So the motion of the upper part of the mantle, the asthenosphere, is actually like a conveyor belt, and the lithosphere, the plates, tectonic plates, are sitting on the conveyor belt, moving with it. So all of us are being transported in the same way. Now here again you can see, as the mantle underneath begins to move slowly, the plates that are being carried on top of it will also drift. So the speed of this motion is a few centimeters per year. Not very much, it's not very fast, but that is a considerable speed of motion, considering the fact that these are huge plates. Alright, the new lithosphere created at the ocean spreading centers cools as it ages and eventually becomes dense enough to sink back into the mantle. Now, you remember I talked about the rock cycle. You see, as the mantle rises, what happens is the lower part of the tectonic plates, the lithosphere, is continuously being made and remade. This flow of the upper mantle will take away part of the lithosphere and make it sink. That means new layer is formed continuously. So this new lithosphere, as the mantle rises up, part of it will go and make the new lithosphere, and some part of it will be carried down to the earth. That means this lithosphere is continuously being made and remade. And that's part of the rock cycle. So it eventually sinks back into the mantle. The part of the lithosphere will sink back into the mantle, and then it rises up and it will go and form part of the lithosphere. So this is continuously being done, the making and remaking of the lithosphere. So such destruction or recycling of the crust. The crust is continuously being recycled. You see, it is taken down to the interior of the earth, then brought up and remade. The crust of the earth is continuously being recycled. So the earth is a dynamic object. It is continuously changing all over. So such destruction of crust takes place along what is called the convergent boundaries. What are convergent boundaries? If there are two pieces of rocks, say like this, all right, move against each other, look at the way they converge and push against each other. So the destruction takes place at the convergent boundaries, where sometimes one plate will sink underneath the other, and the sinking, you can see this one is sinking, and it will eventually go into the interior of the mantle, or we say get subducted. So the recycling occurs at convergent boundaries, where the plates are moving towards each other, and sometimes one plate sinks or gets subducted. What is a subduction? A subduction is the process by which when two plates push against each other, one gets underneath. So this gets subducted and sinks into the mantle. Now let's now talk about the oceanic continental convergence. What is the meaning of oceanic continental convergence? You see, a plate that is an oceanic plate and another plate that is a continental plate, if an oceanic plate and a continental plate move towards each other, this is called an oceanic continental convergence. Now, off the coast of South America, along the Peru-Chile Trench. Now, actually, where two plates, now let me see if you can see that. Where two plates come and converge, where one sinks underneath, is what is called a trench. You can actually see a trench created there. So, off the coast of South America, along the Peru-Chile Trench, the oceanic Nazca plate is pushing into and being subducted under the continental plate of the South American plate. So, if this is the South American plate and this is the continental plate, the continental plate is the South American plate, and this is the oceanic Nazca plate. Now, at the trench, what happens? The oceanic plate gets subducted and the continental plate is pushed up. And this is the reason why these big mountain ranges there, the Andes. The Andes are formed as a result of this. So, being subducted under the continental part of the South American plates. And here I have an illustration of that. The lithosphere, the crust under the ocean, is moving towards the continental crust, gets subducted, and you can see at the subduction zone, you can see the plate has broken and the mantle can now find its way out. You see a lot of volcanic activities near the trench. Now that's the hot asthenosphere coming up. So the oceanic crust moving towards the continental crust results in the subduction of the oceanic crust and the uplifting of the continental crust. So in turn, the overriding South American plate is being lifted up, creating the towering Andes Mountains, the backbone of the continent. You see how the shape of the Earth's surface actually takes place. So strong destructive earthquakes and rapid uplift of mountain ranges are common in those areas. You know why volcanoes occur there? Because of the rupture, and there are hot spots where the mantle, the asthenosphere, can actually find its way up. Alright, the deepest part of the subducting plate breaks into small pieces that become locked in place for a long period of time, but suddenly sometimes it can move, generating large earthquakes. So these pieces that are broken will probably remain silent for a long period of time, but suddenly they can create a jerk, and that is what creates most of the earthquakes. So such earthquakes are often accompanied by more uplift. That means the mountain ranges are actually growing. In most places, the mountain ranges, the Andes, are still growing because of this activity. Now what happens when an oceanic plate converges towards an oceanic plate? Oceanic convergence. When two oceanic plates converge, one is usually subducted and the other is uplifted, again forming a trench. You understand now what a trench is. When one gets subducted over the other, a trench is formed there. Now subduction processes in oceanic plates convergence also result in the formation of volcanoes. Just the same way volcanoes are formed in the case of oceanic continental convergence. You can see here, this is an oceanic plate, this also is an oceanic plate, and in such a convergence, one of them gets subducted and the other gets overridden, and you have the same process, volcanic activities, which will eventually bring out a lot of materials from inside the earth and deposit there, producing what we call an island arc. So over millions of years, the erupted lava and volcanic debris pile up on the ocean floor, and you have islands rising up in there. The submarine volcano rises above sea level to form what is called island volcano, or we call it the island arc. In fact, Hawaiian Islands is such a form of island. Now, such volcanoes are typically strung on its chains. There will be a chain of islands, and they are called island arcs. Now, magmas that form island arcs are produced by the partial melting. You see, the magma that comes up to form the island arc are produced by the partial melting of the sinking plate. You see, when this plate gets subducted, there is tremendous heat generated due to the process of subduction, and that melts to produce the magma, and it is that magma that finds its way through weak spots to form the volcanoes. Now, the descending plate also provides a source of stress as the two plates interact, leading to frequent to moderate to strong earthquakes. Now, very often these areas are prone to, well, frequently light to moderate to strong earthquakes. The Indonesian area, I know we hear about earthquakes in that area very often. That is a trench area where earthquakes are very common in the sea. How about the convergence of continental to continental? Continental convergence. Now a good example can be found in the formation of the Himalayas. The Himalayan mountain range dramatically demonstrates one of the most visible and spectacular consequences of plate tectonics. When two continents meet head-on, that is a continental plate, the Indian plate, and the Eurasian plate, both are continental plates. Now, none of them wants to budge. None of them wants to subduct. Both will fight. And what happens? They will buckle up. So, when two continents meet head-on, neither is subducted because the continental rocks are relatively light, like two colliding icebergs. They resist the downward motion. So when two continental plates meet, they resist the downward motion. That means they're going to buckle up. Is that right? They're going to buckle up and rise. Well, now instead the crust tends to buckle and push upward or sideways. And there you are. You see, the continental crust and the continental crust will meet, it buckle up and rises, and look at the mountain ranges that are produced. Mountain ranges, high plateaus. In fact, the Tibetan plateau is a good example of this. Now this is the Indian plate, very old rock, and this is the Eurasian plate. And there you have the great big meeting, and you got the big mountain ranges produced there. The collision of India into Asia 50 million years ago caused the Eurasian plate to crumble. You see, the great big meeting caused big crumbling of the Eurasian plate and override the Indian plate. Actually, because the Eurasian plate crumbled, it overrode the Indian plate. So the Indian plate did not buckle a lot. The Eurasian plate overrode the Indian plate. After the collision, the slow, continuous convergence of the two plates over millions of years pushed up the Himalayas and the Tibetan plateau to their present heights. And that's a magnificent sight, is that right? And the Himalayas are still growing because the convergence of the plates are still continuing. That's right. So the rising Himalayas and the rising Tibetan plateau as a result of the Indian plate and the Eurasian plate. The Eurasian plate crumbled into pieces and overrode the Indian plate. Most of this growth occurred during the past 10 million years. The Himalayas, towering as high as 8,854 meters above sea level, form the highest continental mountains in the world. What are transform boundaries? You see, so far we talked about what happens when an oceanic plate and a continental plate meets. What happens when an oceanic plate meets an oceanic plate? And what happens when a continental plate meets a continental plate, right? Now, all these meetings occurred when they meet head-on and press against each other. In the process, one tends to subduct and the other tends to override. Now, transform boundaries are different. Now, if these are two plates, transform boundaries are boundaries where plates move. See that? Can you see how they're moving? They move one towards the side. They will not press against each other, but they pull, or they actually go sideways. Now this kind of a boundary is called a transform boundary. So the zone between two plates sliding horizontally, is that right? These two plates are now sliding against each other. They are not pushing against each other, but sliding against each other. But there can be considerable interlocking, and there are broken pieces of the plates. Those broken pieces will then shudder many times as the sliding continues, and that will create considerable earthquake regions there. So the zone between two plates sliding horizontally past each other is called a transform fault boundary, or simply a transform boundary. Now, most transform faults are found in the ocean floor. They commonly offset active spreading ridges, producing zigzag plates. Because they slide against each other, they tend to zigzag and are generally defined by shallow earthquakes. But there is an example where it actually occurs on continent. A few occur on land. A good example is the San Andreas Fault in California. If you look at this, the San Andreas Fault, the relative motion of the Pacific plate. You see, this is the Pacific plate moving that way, and this is the North American plate moving this way. So they are sliding past each other. The Pacific plate moving in that direction, and the North American plate moving in the opposite direction. The San Andreas is one of the few transform faults that is exposed on land. Most of such transform faults actually occur in sea. Now this fault zone, which is about 1,300 kilometers long, it's a very long area, and in places tens of kilometers wide, slices through 2/3 of the length of California. And that's the reason why these areas are very prone to earthquakes. Now along it, the Pacific plate has been grinding horizontally past the North American plate for 10 million years at an average rate of about 5 centimeters per year. Not very fast, but it is quite a good speed to create a lot of havoc in that area. Now look at the trench that is created due to that transform. This is the San Andreas. So the land on the west side of the fault is moving in a northwesterly direction relative to land on the east side, which is moving in the opposite direction. All right. Now, the oceanic fracture zones are ocean floor valleys that horizontally offset spreading ridges. Some of these zones are hundreds to thousands of kilometers long and as much as 8 kilometers deep. So most of these occur underneath the sea. So what is the summary of our present day understanding of the interior of the earth and what it does to the crust? Well, the solid materials of the earth are engaged in a continual cycle of change. The crust is not a permanent structure of the earth. See, the crust eventually gets destroyed and is taken into the earth, and material from inside the earth are brought up forming new crust. So the solid materials of the earth are engaged in a continual cycle of change. It changes continuously. Oceanic crust is subducted, melted, and partly returned to the crust as volcanic igneous rocks along continental plates and boundaries. So in the last lesson we talked about igneous rocks. What are igneous rocks? When magma from underneath rise up through the hot spots, they cool on the surface, they become igneous rocks. Now these igneous rocks, with years of weathering and destruction and breaking into pieces and get washed away by rain and wind, ultimately end up in seabeds as layers and layers of sediments. And these sediments are subjected to high pressures and temperatures, and in millions of years it becomes rock. In other words, it becomes part of the tectonic plates. And these tectonic plates are transported by the motion of the upper mantle. And sometimes the crust, this part of the crust, can sink back. See, look at that. The rock that is formed can now be taken back into the earth and recycling. So the crust of the earth is continuously being recycled. The earth is a continuously changing phenomenon. In other words, there is nothing static about the earth. Earth is a very dynamic object. Every bit of what you see is being made and remade. If you come back and look at the surface of the earth after, say, 50,000 years, it may not look the same as we see now. It's continuously changing with not these natural forces. Other parts of the subducted crust become mixed with the upper mantle, returning as new crust at diverging boundaries. So the crust gets carried to the inside of the earth. From inside, the materials come up and build new crust. You can see that cycle is continuously happening. The materials of the crust and the mantle are recycled back and forth. This is a continuous process that is happening. And this is what we call the dynamic nature of the Earth's interior and the crust. Well, what we will be doing as we go on is looking at this dynamic nature. Earth is a dynamic body and it constantly undergoes changes. Well, we will denote a couple more lessons to talk about some of these changes, all right? And I will see you for the next lesson later on. In the meantime, it is a good time for you to go and review and do some homeworks, all right? I will see you for the next lesson later on.